Hello, everybody. My name is Walter Dort. I'm a program manager in cloud and AI security. And I have the honor of introducing our next speaker. So before we get into that, I just wanted to remind everybody, this is all public information. You can feel free to share this online. Use the hashtag BlueHat. And all the speakers' handles on Twitter will be on the agenda that you have. So without further ado, we'd like to introduce Gabe Bassett. He's a senior information security data scientist at Verizon Security Research. So there you go.
Okay, let's see. It works. Okay, let's see. Are we up and going? We good? Yay, we're good. Okay, so I'm Gabriel Bassett, and this presentation is going to be why not graphs, or also why not graphs. We're going to cover both of those. Before we get into it, this is the disclaimer. This is my opinion, and so I do a lot of data-driven security talks, and this is going to be about kind of my opinionated view and experience with graphs. It's not academic fact in any way. And that doesn't mean that my opinions are wrong or bad, just that the only evidence is my experience. Now, things I'm not going to talk about are all this stuff. These are all important things when it comes to graphs, you know, nodes and edges, the types of graphs, things like that. But there are also things that you'll be able to go back and look at, and maybe some of the other speakers will cover them. This is going to be primarily about kind of the process I went through with graphs. And so, you know, starting out with who I am not going to introduce or show you a tool like Colin is. I am not going to do this incredible, awesome presentation that just flows with a wonderful accent the way John Haas is. I'm just another data scientist doing stuff. But I've been doing stuff with graphs for a long time. I started back in 2011 in a room that was kind of like this. It's one of these government rooms, right, that doesn't have any windows. This one was underground. It was like, had room for like 120 people, and there's like 10 people in it. And I had a problem because I was getting all this cool information, right? This cool intelligence about who is attacking what, where, and like all these super awesome details. And the problem was I couldn't do anything with it. Like there's no way to take that information and make it actionable to the broader audience. And this was really frustrating me because I wanted to make all this information very actionable and be able to make use of it. And so one day, it's like the end of the day, I'm walking past one of my friend's cubicles, and he knew the problem I was having. He goes, hey, you know, my company had this project that we did a year or two ago, and it used these things called graphs. And his company, because he was a contractor, he's like, you know, I don't really know a lot about them, and the project didn't really go anywhere, but you know, it kind of seems like something that might fit what you were doing. And so I didn't know anything about graphs in the mathematical sense at the time, and really neither did he. And so we did what any good researcher would do, and I went and looked him up on Wikipedia. And you know, that's a good starting place. And the more I learned about them, the more I realized that they were something that I really liked. It made a lot of sense to me. And so now in the government, for those who have worked in the government, you realize you don't just get to go install software. But what you do get is you get Microsoft Office. And so I went and implemented Bayesian network inference in Visual Basic in the back of an Excel spreadsheet. We put the nodes and edges in here, and now you can put in like the place and like an indicator and a person, and you could have them linked up, and you could, you know, do inference through it. And I was super proud of this. I wasn't a programmer at all at the time. I showed it to my boss, and she said, Gabriel, you know that we don't make tools. This was not the high point of my career. But I kept going. I left, did a little work, invented new stuff, got another job. But the graph stuff stuck with me. And so, let's see. The next part is to figure out when to use graphs and when not to, because a lot of times graphs either make sense to people or they don't. And this is kind of an example from Graphical, which we'll talk about later in the day, I think after lunch. You can think about data in kind of two forms. It can be a graph or it can be tabular, and people kind of lean one way or the other. And one thing I found over time is that a lot of people, the graph is just never going to make a lot of sense to them, working with it directly. But on the other hand, there's a lot of people that once you learn about graphs, it's just like, it's mind-blowing. Like, it's like, this explains everything, right? The whole world, it's all graphs. And it certainly is for me. Like, I understand things that way. But that's kind of a problem, because the reality is, while everything can kind of be explained that way, it's not always a good idea. And so I saw this kind of marketing slide in a blog a couple days ago, and I kind of like it because, right, databases, oh, there's no use. Graphs, they do everything. And the only thing I can say is if you think that there's no trade-offs in using graphs, that means you just haven't used graphs. There's a lot of trade-offs in using graphs. And so you need to understand where to apply them and where not to apply them. Now, the things that really affect where to apply graphs and where not to are kind of, one, how is your data structured, and two, how are you going to be querying it? And so if your data is a lot of tripoles, so A is related to B. We just heard in the last presentation about relationships. A is related to B, and you've got a lot of different A's, and you've got a lot of different B's, and they're spread out, and none occur a whole lot. Maybe it makes sense to structure your data as a graph. And so in my original problem, I had all these disparate things like location data, data about an individual, technical data. And it was all very disparate, and so it made sense to structure it as a graph. In my current job, we structure a lot of our breach data as kind of hierarchical JSON. And any individual record may have only a subset of the relationships. And so we're still currently able to flatten it out due to a couple peculiarities about it. But it may make sense to go and change it to a graph in the future. On the other hand, if your queries are very graph structured, it makes sense. And so, like, who here has heard the term "think like a vertex"? Anyone? Yeah. It's from the original Pragel paper from Google. And what it means is that your algorithm starts like at a node, and then it looks at its neighbors and it makes a decision, and then it moves to another node and makes a decision there. And you get kind of this sequential query through your data. And so if your queries are very much like that, like A going on to B, going on to C, going on to D, a lot of times that kind of lends itself to a graph-based query. Like in the last talk, we weren't necessarily querying graph data, but we're using a very graph-structured query to get to the data. And that's why the graph structure helped in that case. Now, on the other hand, sometimes graphs are not the best choice. And this is one of my ugly graphs. We'll talk about visualizations later, but this is just demonstrably ugly. So to understand when not to use graphs, you kind of need to go back and think that even though you may think in terms of graphs, your computer doesn't necessarily, right? Your computer's memory is sequential. It doesn't store it in a graph the way your mind does. And so traditionally, there's a couple ways to store it. You can store them as linked lists, which are slow to write, and you can store them as matrices, which are slow to read. They all have their disadvantages. And this isn't to say that this is like the state of the art. Even years ago, Georgia Tech had a program called Stinger, which did linked lists, but it put like blank pieces of memory in the list so they could shift data back and forth much more quickly. And so there's probably a bunch of stuff that's been done to improve this, but your data is still being stored sequentially, even if you are interfacing with it, and even if your visualization or storage of it is as a graph. And so because of that, you need to think that since it's being stored linearly anyway, maybe it makes sense for me to store it that way and to actually work with it that way. Because I think that we mentioned in the last talk relationships, and as you start to think in terms of graph, everything starts to look like a relationship. And then we go, well, if it's a relationship, it must be a graph. But right, in a database, like a row in a database is called a relationship for a reason. And if your data is tabular in nature, there's no reason that you need to maintain the relationships explicitly, right? Your relationship may be maintained by just having a bunch of sequential blocks of memory, so that this entire column right here is a bunch of spots of memory, and then followed by this one. Oh, come on, laser. This one, and then this one, and this one in the memory. And to get to each, you just take your offset of your row, and then you add the length of the vector, and you can quickly move through memory. In fact, something like this stored in R, these strings are pointing to a global cache, and so they don't even take up a whole lot of additional room. And this is just a Boolean one. And so you're not necessarily wasting a lot of memory, and potentially you're gaining a lot from a structure perspective. On the other hand, if your queries are very verb-based, and so I use like the dplyr verbs down here, but you could also use SQL verbs. So select, where, from, things like that. If your query fits that structure and isn't so much vertex-based, you may want to be querying using tabular data. It may make a lot more sense because it's a lot easier to structure and to do some of the more complex questions. It'd be very hard to ask what's the median of each of these different sets of data if you're doing it through a database versus doing it over a vector. And over a vector, it's particularly easy in that you can just rip straight through memory. And so if you look at like examples of kind of the differences, right, a lot of our log-based analysis works well this way. And even though we can do really awesome things using graphs, a lot of times we shouldn't be necessarily using graphs if it doesn't make sense. On the other hand, if our graph is something like, if our data is very walking through it, like who here is like looked at OpenDNS Umbrella, right? They store kind of these tuples of, a domain is related to an IP, and an IP to an ASN, and ISN back up the chain to Whois data to people, and then back and forth. And you can flow reputation through that graph. And that's just kind of an example that is used in many other places. And so that does fit very well with kind of the graph-based query. And ultimately, the thing to remember is that there really isn't any graph, right? In the Graph API example in the last talk, right, we're using graph type queries to query not necessarily graph structured data, and that's okay. Because at the end of the day, we're just looking for relationships, and it's all about, what structure gets us the most efficient and easiest connection with our data. And before I move on to the visualization stuff, I want to just quickly hit on properties. Because as soon as you build a graph, the next thing you want to do is you want to add properties to your nodes, because you realize you left something out and it doesn't fit your scheme anymore. And this works in a lot of cases, but there's a lot of cases where it doesn't work. For example, if you start realizing that it's okay if it's like a column in your tabular data. Like you put something on there that you're just going to pull back in as you do your queries. But if your queries are consuming your properties, a lot of times that's more like adding a table to a database or adding a dimension to a tensor. And then that's going to slow down your entire graph query because you're not really transversing the graph structure anymore, you're transversing the data itself. And so if you find yourself putting properties on nodes and then using those properties as part of your query, it's a good sign that you may want to look back at the structure of your data. Now, after you start using a graph, the next thing you're going to want to do is you're going to want to visualize it. Because we all love graph visualizations because they look really cool. The problem is sometimes they're good and sometimes they're bad. And so good graph visualizations, not necessarily pretty. This isn't pretty, but it's good. And it was the quickest example that I found when I was looking through the body of graphs I had. The reason this is good is it's got 2 to say 30, 40, 50 nodes, like 3 to 4 dozen nodes is kind of a good upper limit. For not highly interconnected data. You can see all the edges, you can see the labels on the nodes. And when you have a graph like this that has a small number of nodes, you can see the labels and you can read the edges, you can kind of look at the relationship between these. What this is the relationship between actions and attributes in our public various community database of breaches. And so incident happens, an action happens, it compromises an attribute, and then that can lead back to another action, and eventually the incident ends. And this is something that, like, if you're comfortable with graphs, if you think in terms of graphs, like, you can look at this and you can get information from it. The next type of graph visualization that I don't see a lot of, but I really wish I'd seen more of, are structural visualizations. So you couldn't read any individual piece of information off of this. That's just obvious from the beginning. But you can read structure. Does anyone want to take a guess at what kind of structure they're seeing here? Yeah, it's a tree, it's a topology. This is a network topology from a large company. And what it is it's the hierarchy of the routers and switches in the IP space. And the cool thing about this is if you were to take this and you were to take different organizations and lay their data out in the same way, same data, same way, you would start to see the structural differences between the individual companies by looking at the differences, as long as you laid them out the same way and structured the data the same way. And this is one of those graph visualizations we very rarely see in practice. But I think it's a very powerful one, looking at the differences in structure of the graph. And then there's just telling a story or making a point with the graph. This one, there's nothing you're going to gain from just looking at it. It's kind of pretty, but it really makes a specific point. And so I used to work at this organization where the CIO had his all hands, and he was always running a little behind. And so his VPs would be sitting in there kind of hanging out. And I would print these things out, and I would take them in to show to the VPs. And so I'd say, hey, what this is this is the connections between everything in your network. This is a computer talking to another computer. And you know what? That lime green one right there, that talks to more than anything else in your network. You want to guess what that is? Anyone want to take a guess? That was their guess as well. And it's a good guess, except they had 50 domain controllers. And so that load was, it turned out, spread across a bunch of systems. That is the PAC server. Anyone know what a PAC server is? Proxy autoconfig. That tells every single one of every computer in your entire network how to talk to every other computer. And so if you control that, you control how all the computers in the network talk to each other. And that was the most central server because they had one PAC file server. And it turned out that that server wasn't really high on anyone's security list, right? Because it just kind of sat off the side and did its thing. That's a profound message. That's important, and that's a significant thing to know. Another was this. And so we took kind of the same connectivity graph, and we infected one system at tick 0. And then we're showing tick 1. And so at tick 1, every tick we spread the infection at like a 70% infection rate. In tick 1, not a lot gets infected. At tick 2, it's starting to look like a lot. At tick 3, it's the majority of stuff. And at tick 4, it's like almost everything, right? And this was explaining the story of here's what happens if you get something that's going to spread heavily inside your network. Here's how quickly it's going to take over, right? And this is, again, we handed out kind of as a handout. This was a significant thing. It made a big message, and it explained the need for segmentation and control over how individual systems talked internally. Now, on the other hand, there's lots of bad graph visualizations. And I'm going to apologize to Theo up front because this is an absolutely beautiful graph. It's from a tool called Open Graffiti that some folks on the OpenDNS team made, and it makes these just beautiful 3D visualizations. The problem is I cannot figure out for the life of me how to actually use this. It's beautiful, but it's not necessarily actionable. And every single person in this room who's ever done anything with graphs has made a visualization like this. Something that was beautiful, and you want to show it because it's so awesome, but you can't do anything with it. And so as users of graphs, we need to be aware that that happens. And we need to be prepared to understand and to explain to people like, look, we're showing you something cool, but let's get to the actionable stuff. Because people who are not used to using graphs look at this and they go, OK, what am I going to do with it? And they feel like they're failing when they can't come up with some divine insight from something like this. And then they get frustrated with graphs and they go on. And then sometimes you get to graphs that are just so big that you're never going to visualize them well. So let's see, this type of graph, you can use this up to maybe 300,000 nodes or so, as long as they're not highly interconnected. But once you get over that, your graph's going to start looking like this. Or if you've got a highly interconnected graph, it's going to look like this. And it's going to be ugly, and you can't do anything with it, and there's no point in showing it to anyone. This is one of my graphs, which is why there's no citation on it. I make ugly graphs, too. But there's things you can do about it. And so first thing you want to do is filter, right? This is, who here is familiar with Bloodhound? Yeah, good number of people here. That's good. I was talking to Stephen Few, who's a visualization expert at a conference years ago. And I asked him, what would you do to make graph visualizations better? And because, right, with normal visualizations, bar charts and point charts, you can do a lot. You can scale axes. You can, improve how the tick marks are laid out. There's a lot you can visually do to make a graph better. make a figure better. With a graph, his answer was there's no good solution. You're not going to do any of those things to make it look better. What you can do is you can filter and you can group. And so you see that they're grouping a couple of nodes together here, and then the edges associated with it in and out are grouped. You can filter. These are what make a graph look better. If you have a large graph, and you're going to want to read nodes from it, you're going to have to get down to those 2 or 3 or 4 dozen nodes. And you need to be able to group nodes to be able to do that. Also, I think that interactivity plays a big part. The ability to mouse over a node and see information about maybe here's how many nodes are grouped below it, or here's its labels or its properties, things like that. Interactivity helps a lot, and it helps keep the graph from being uncluttered. Also, animation can help a little bit. In fact, there's some really cool tools. This thing just came out like a couple weeks ago, I think. But it's a tool that's all about grouping in graphs. And you've got these really awesome subgraphs underneath here and labels. It's really cool how they are visualizing the groupings. Now, the question then is, how do you determine what to group? And sometimes it's easy because everything has the same property. A more generalized solution, I think, is entropy. And I really this is from 2013, from AT&T, I think, yeah. These maximal entropy summary trees. And the idea is that you want, as you roll up, you say, I want to have at most 30 nodes or something. And so what you want is the maximum entropy between nodes so that you're grouping like things into each node. And I think this is a great way to do it. This works on trees. In fact, there's an R package for it. I've written an algorithm that will do this in more generalized graphs, and this happened back in 2013, so I seriously doubt I'm the only one who's ever bothered to try to do that. So I'll bet that now you could find multiple implementations to kind of use entropy to group your graph. The other portion is you need to think about how you're going to lay it out. I literally just took whatever graph I worked on last in Gephi and opened it up and laid it out a half dozen ways. And some of these are far better than others, right? Let's see. This one, the middle one right here, I think I dislike the most. Because you notice there's this very specific cluster over here of interest. I don't even remember what this graph is, but this is the interesting portion. And in fact, up on the upper right one, it's off screen because it got pushed off so far from a force atlas perspective. A lot of times we default to kind of force-based layouts, and sometimes they work and sometimes they don't. It's important to explore the visualizations you have available and to try out different ones. In fact, at the Viz 2019 conference, which is, I think, going on this week, someone is presenting a generative model to do graph visualization. And so the model tries to maximize and minimize some specific values, and it gives you a range of visualizations. And then you get to go and kind of sort through and pick which ones make the most sense for your data, which I think is really cool. But ultimately, the way to visualize your data in your graph may not actually be to visualize your data in your graph. A lot of times, the right solution is tabular visualization of the analysis. And so we saw that in the last presentation where we were using a graph query to pull back data, but there wasn't a graph that was demonstrated. It was shown in tabular results, which is perfectly fine. In fact, this guy kind of had the same thing. He loves using Bloodhound, but he's using the same queries over and over again, so why even bother working directly with the graph? Why not just dump out the tabular data and work with that, which is, again, pretty easy to work with. And so moving on from that, now we're going to walk through some of the examples that I've done with graphs, particularly in things like the DBIR over time. And we'll see kind of the evolution of kind of how mentally I've worked with them and how I've thought about, or how they've changed kind of for me over time. And they started back in 2014. Jay Jacobs made this visualization and put it on the cover. This is a graph overlaid over the PCA layout of the patterns, or the clusters that he did that year. In the same year, I joined the team, and I took the DBIR data, and I wrote some heuristics that let me build a graph from it. And again, this is the same one we saw earlier in the pretty graph, except it's got way too many nodes to be useful. Your attack starts at the green node. It goes to a red action, and then that compromises a blue attribute. And then the attack could end, but it could bounce back and forth over and over again, and kind of finally until it comes to this end. And this is incredibly profound, right? like you can do some incredible calculations through this. You could go take this graph and figure out what mitigation stops the most paths between actions and attributes. What can I do what's my single best mitigation for all the potential attacks? You can ask, what's my single best mitigation for the most likely path through the graph from start to end? And how does it change over time? If I mitigate one thing, what's the next thing I mitigate? And what's the next thing I mitigate? And we'll see an example of that here in a couple slides. You can even go and say, OK, let me compare two sets of mitigations. I'm going to mitigate this set of nodes, and I'm going to mitigate this set of nodes, and I'm going to see which one performs better. So if I'm a CISO or someone, I can say, hey, I've got two sets of mitigations I can implement with the budget I've got this year. Which one of those is likely to give me the better result? And I built this into a web app that may still be running. I haven't checked it in a year. But it provides this really interesting way of looking at graph. The reality is this graph isn't useful. I showed it to my colleagues, and they go, it's a dream catcher? Yeah. Even though you can interact with it, you can mouse over the nodes, and it'll give you the label. It'll tell you what they're connected to. This really doesn't do anything more than anchor the concept in people's minds. You can't trace an individual path through it, which is what people always want to do with graphs. Now, in 2015, we worked with the European Union. They put us in touch with the Trespass project, and they put us in touch with the Lust design firm that was working for them from The Hague. And their suggestion on how to visualize graphs was this, right? And this is better, right? It's got a smaller number of nodes. It's an arc plot. But still, this isn't actionable. You can't do anything with this. This data would probably be better as a pair of bar charts, because you can take the nodes and you can build bar charts out of them, and you can take the edges and build bar charts, and it'd be much more immediately actionable and useful to people working with it. Even though this is interactive, again, you can mouse over this stuff, you get all sorts of cool stuff from looking at it. And so as we moved on to 2016, instead of showing the graph so much, we showed the analysis. We still have that picture in there, but this time we showed the analysis that we were doing on that kind of the Dreamcatcher graph. And this is the kind of figure you got. And this is profound. Like, this could still drive people's security projects and programs, because it turns out that there's really only two types of attackers. There's the attackers that if they fail, they use the same attack on a different target. Then there's the attackers that if they fail, they use a different attack on the same target, which is you. This is 85%. The first one is 85%. The second one is 15% of all attacks. The second one are the advanced attackers. And the reality is, if you mitigate that one path that these attackers are trying for the first type of attacker, they go on. And so your first couple mitigations, and these are based off of incidents, and so you see things like DOS that don't cause breaches. They just compromise availability in here. But you get the same thing if you were dealing with breaches. The first couple mitigations make a huge impact, because you're effectively eliminating the 85% of attackers who won't try a second type of attack against you, because they all use the same type of thing. Once you get past that, the last 15 is incredibly hard to mitigate. And the reason is because if you get down into here, if you mitigate step one that they try, they don't go on to the next target, they just try the next dot. And so you have to remove all the things that they could potentially try to get rid of that attacker. And so it becomes very expensive. You don't get any additional benefit from these until you've mitigated a lot of them. And this is something that could drive an organization's security strategy. Mitigate the 85% that gets us a big return, and stop spending the same amount on all these little things that get us almost nothing in return. And so we moved on in 2017. In 2017, we didn't do any graph stuff. We had other stuff to do. But we came back in 2018. We put an arc plot on the cover, which I thought looked really cool. You still can't calculate anything off of this. This is just pretty. But it's on the cover. What we did do in the back, though, was much more useful. And we did this with Graphistry, and I think Leo will be up here later talking about some of the stuff he's doing. But what we tried to do is we started to get away from showing graphs, because we realized that you can't show graphs to people because people want to see the paths. They want to say, here are the lines that I follow to understand what's going on in this. And they don't get that from a graph. And so instead, we started to go to a much more path-based figure. And this kind of starts to look like a Wardley map, which I'm sure John is likely to mention during his presentation, in that you have a x-axis and you have a y-axis. You have points, and you can start to figure out that this goes this way, and kind of here's how things pass. And the thickness tells you kind of the direction to go. And this is very useful. This is actionable. This is a functional visualization of this graph. The problem was it was still very threatening to people. People who are used to seeing bar charts or scatter plots, this is a complex figure to try to consume. And people still had trouble reading it. And so from there we moved on. And in 2019, we went all in on paths. And so again, on the cover, and then inside, we used overplotted paths. And this is where I'm focusing a lot of my energy now in visualization, is to try to figure out how to use overplotted paths to communicate what's in a graph. Because, and people still, they want to read individual paths. They want to know what's that one path there. And it's just something about the way we think, but you can still get something from the overplot. You can see that you get this kind of overarching narrative. Like most attacks are short. The long ones tend to be more hacking and malware based. Social attacks start a lot of breaches, both long and short. You can gain a lot from this. More so, you can plot it over other things. And so if you look at breaches in accommodation, you can say that they are much more likely to be malware and hacking and longer than the majority of breaches. And that's because accommodations breaches normally are malware sitting in RAM and scraping RAM for credit cards. And so it takes a much more complex attack to accomplish. You can even look at the shortest path, which is, or the most common path, which is always going to be short. Because the longer it is, the more likely that it diverges at some place. And then finally, I'm going to end up with a non-DBIR type project that I worked on. And the main reason is to talk about schemas. Because schemas try to represent the world. And the security taxonomy that John and Dennis did is excellent. It's beautiful, but it is complex. And as you try to represent more complex portions of the world, you're going to get much more complex schemas. And it becomes more complicated to use them, and your graph becomes overburdened. And so I went the other way and said, I'm going to try to create a simple schema. Because obviously, simple schemas should be able to store anything, because our brains store anything, and they don't have some complex schema in them. And really what we came up with, or I came up with, was kind of two different structures and two different graphs that are related. The first are context graphs. Context graphs relate facts, right? This building is on a street. The street is in a city, things like that. And the other portion are action graphs. This action will lead to this effect. And then by pairing those together, we could then try to make decisions through it about what was happening in the world around us, or what was likely or wasn't. And so I built out the graph, put a lot of facts in it, and you get this beautiful kind of structure graph. Again, you can't calculate anything on this. This is just pretty. But it's meant to make the point that it mimics, this graph tries to mimic the way a brain works, because brains are going to be the most dense, the most power efficient calculation systems that we have for the size. And so as our graphs try to grow and as we try to make them more complex, looking at how brains work is a good place to start. And by the way, I don't have enough time to do the demo or anything of this. If you want, you can see the video from 2015 when I demoed this at B-Sides Las Vegas. That link, or you can go read the blog post. And I probably should start wrapping it up. I'm about at time. So there's only these two things ultimately through this whole presentation that I want you to take away. The first is how important the structure of your data and the way you're going to talk to it are in using your data. And the other is communicating it. Because it's going to be those two things that are going to drive the success or failure of graphs within your project. And so with that, well, before I open up to questions, I know this is like a super stale meme, and I should have used Galaxy Brain for it. But it's my presentation. I can do what I want. So with that, questions? Any questions? I know I should ask and then give you some time to actually think about them. But I actually may have saved myself just enough time for questions, which I really do. Yes?
There's actually a question from Twitter. They want to know what tools you recommend for graphs, for building graphs.
So if I was starting out, Gephi is a good one to get started out with, because it lets you very easily visualize your graphs. And a lot of times as you start working with them, you need to see what it looks like and what your data looks like to kind of anchor it in your mind. And Gephi is one of the best ways of doing that. When I like working with graphs directly, I like using NetworkX. When it comes to, even as you get into big and production graphs, there was, just to make a point, some guy years ago, as graph databases were starting to get big, he kind of said, look, you really don't need the overhead of it. And to prove a point, he took like the largest multi-billion node graph that existed that you could get your hands on, and he wrote a graph tool in C with a Python interface and parsed the entire thing on a single host. And so from a scale perspective, even as you get bigger, a lot of times it's better to work with the graph in memory on a single host than to try to use the distributed systems, because they have all sorts of performance issues that you'll run into. And it's very unlikely that your graph is so big that you won't be able to parse it on a single host. And another secret about that is you don't have to store the data as a graph, right? You're trying to keep relationships. So you can store the data tabularly, build the graph when you need it in memory, do your calculations over it, and discard the graph. And I've had someone tell me that that's what a lot of very, very, very large companies actually do. Ones that are based around their graph, they don't actually maintain their graph. They just build it when they need it, analyze it, and dump it. Yeah. Here, give you a mic here.
Name's Will. In your use of graph in the DBIR, what is the most surprising thing to you that you found out for this year?
This year. That's a good question. I don't know if any of the insights this year were surprising from a graph perspective, because I've seen it so many times over. I think for others looking at it, it would be, there is a good one. So I think the biggest surprise is that most attacks are short. The paths are almost always short and very, very rarely long. But the other thing I think is really cool is that specific actions start breaches, specific actions continue breaches, and specific actions end breaches. And so breaches almost never start with malware, which makes a lot of sense if you've thought about it, because the malware had to come from somewhere. But if you haven't thought about it, it's like, oh, gee, if I see malware, maybe that means I need to look back in time, where it came from. On the other hand, breaches almost never end with social attacks. And so if you're seeing a social attack, it means there's more coming. And so you can use what you've seen. When you start thinking in terms of paths, you can use what you've seen to kind of guess at what you haven't seen as part of the breach. Does that answer your question?
Yeah, that's great.
Sweet.
Thank you.
Any other questions?
Got time for one more.
Okay, I got one more. Way back, yeah. Mike's coming.
Yeah, so first of all, thank you for the talk. On the analytics side, what are maybe the starting points you'd recommend folks for, especially for security applications, of areas that would be most useful to start with, similar to what you said on the tooling side, but more on the algorithm side?
So you said on the query side rather than the algorithm side, or the what
Like
side?
page rank and centrality, that kind of stuff.
Oh.
What do you find actually useful for security practitioners, if anything?
So this isn't actually an interesting question, because I think a lot of times, we get into graphs, and then it's like anything else. You see, you'll initially see these specific algorithms like breadth first search and depth first search and page rank and centrality, and all these kind of common algorithms, and you feel like, oh, I saw those, but that must just be the beginning stuff. There's probably much more complex stuff. And I mean, there is complex math you can use against graphs to kind of determine more interesting stuff. But the reality is, a lot of times, the simple stuff works, And so running something like PageRank just basically does random walks around a graph, and kind of helps you determine what's most important in it. Centrality is kind of a different way. A lot of times it's eigenvector centrality, which is similar to PageRank anyway. But it's figured out what's the most important node in my graph, what's central to it, or how do I get from point A to point B. Another one is minimum cut, which says what do I need to remove, what's the minimum edges or nodes I need to remove to separate two portions of the graph. But start with that simple stuff. Whatever tool you're using, just start with the algorithms it has involved, and instead focus on the question you want to ask the data, not so much, am I trying to use the most advanced algorithm? So with that, that's probably my time. Thank you.